Hi, my name is Karolina. I'm a virology PhD student, and because I believe virology is full of fascinating stories, I decided to share some of them. I spent a good portion of the last episode telling you that HIV cannot be cured, and our best option is to keep it under control with medication. But here's the thing. I wasn't telling you the whole truth. In a handful of cases, people have been declared cured of HIV. The first was known as the Berlin patient, and since then fewer than 10 cases have followed. Today I'd like to share their story and explain why we shouldn't hold out hope for a miracle pill. Because this cure isn't some simple medication. Instead, these people received a high-risk bone marrow transplant from a donor genetically resistant to HIV. The first patient ever cured of HIV infection was introduced to the world as the Berlin patient. This nickname was given to him because he lived in Germany, in the city Berlin, at the time he was diagnosed with HIV. And for several years his identity was kept private. But in 2010, he felt ready to step out of anonymity and share his full story, so we could put a face and a name to the nickname. So the Berlin patient finally became known as Timothy Ray Brown. Timothy was diagnosed with HIV in 1995, and at the time, there were no signs that he would one day rewrite history. He started to take the AZT drug, which was one of the earliest available treatments, but unfortunately, AZT had severe side effects and it wasn't terribly effective in the long run. But luckily for Timothy, only 1 year later, better drugs were developed, specifically the protease inhibitors. And thanks to those, he was able to take effective medication, and for the next 10 years, he lived pretty much a normal life. But while his HIV infection was under control, he was unfortunately struck by another medical emergency. Timothy started to feel exhausted all the time, he became weaker, and eventually he described that he couldn't even ride his bicycle for 1 mile. So his doctors were trying to find out what was wrong, which took a while, and eventually a bone marrow biopsy revealed that he suffered from leukemia. He had to start chemotherapy, which was associated with many complications, including infections, renal failure, and at one point he even had to be placed in an induced coma. During these complications, his doctors also interrupted his HIV therapy. But what followed at this moment was very expected and completely typical scenario after HIV therapy is interrupted. Soon after, Timothy experienced a viral rebound, and in his blood was detected high number of copies of HIV virus. So the doctors, of course, immediately restarted his HIV therapy, and after 3 months of treatment, his viral levels were under control again. During his leukemia treatment, the doctors were also preparing for the possibility that chemotherapy may not be enough, and that Timothy might need a stem cell transplant. So the doctors took a sample of his blood and checked with a donor bank to see if there are any matches for the possible transplant. Finding a match can be difficult, but in Timothy's case he was quite lucky because he had almost 300 potential donors. And this gave his doctors an idea that not only could Timothy receive a transplant to save his life from cancer, but they could also try to use this transplant as an opportunity to cure him from HIV. This would only be possible if among those 300 potential donors was one with immune cells resistant to HIV infection. So as part of the leukemia treatment, it would be possible to replace Timothy's infected and sick immune system with one that was healthy and resistant to HIV. So how could such a thing be even possible? To enter a cell, HIV needs a molecule known as CD4 to act as a receptor. However, early on it became clear that CD4 alone wasn't enough for the virus to infect cells. Epidemiologists noticed that some people didn't get infected with HIV, even though they had many risks and exposures. For example, it was noticed that some sex workers seemed to be resistant to the virus. So something was protecting these people from the infection. Scientists isolated the lymphocytes of these resistant individuals, but they didn't see any difference in the amount of CD4 molecules on the cells. In other words, these resistant individuals had just as many CD4 receptors as anyone else. Yet the virus still couldn't get in. The reason is that HIV requires two different molecules to enter human cells. Yes, the CD4 receptor, but also a chemokine co-receptor. Most HIV variants use a molecule called CCR5 as this chemokine co-receptor. And some people have a specific genetic mutation called CCR5 Delta32, which means that there is 32 amino acid deletion in the CCR5 gene. If a person inherits both copies of this mutated, shortened version of the gene, that is, if they inherit the mutated variant from both parents, the receptor is not functional. And as a result, HIV is unable to use this shortened version to enter cells. And actually, even if you only inherit one mutated copy, that is, if you're a heterozygote, you still get at least some level of protection against AIDS. Heterozygotes show at least partial resistance, and their infection progresses to AIDS more slowly. During our school immunology course, we actually tested ourselves to see whether we carry the wild-type CCR5 gene or the mutated one. So we basically did a cheek swab to collect cells, isolated the DNA, and then ran a PCR with primers flanking the 32 base pair deletion in CCR5. And finally, we checked the band sizes on the agarose gene, which told us if we had the wild-type allele or the mutated one, or both, of course. I remember that in our group, there were no Delta32 homozygotes. However, I turned out to be a heterozygote, which is at least a little cool. At the time, there was a rumor going around that all the homozygous Delta32 carriers are always exchange students from Spain. Which honestly, I'm not sure how accurate that rumor was, because based on a distribution map I've seen in one paper, the frequency of this mutation is actually higher in the Czech Republic than in Spain. Overall, this mutation is especially common in European populations, where its frequency is around 5 to 15%. And it's also estimated that about 1% of Caucasians are homozygous for Delta32. Another story I heard was that the same test was also being done with high school students to show them how lab research works. And in their case, they were only told how many people in the class had the mutation, but not which specific students carried it. You know, because there was some worry that telling teenagers they were resistant to most HIV strains may encourage some riskier behavior. But let's get back to our Berlin patient. As I've said, his doctor had the idea to screen his potential stem cell donors for the CCR5 Delta32 mutation. So they started screening donors, and on the 61st attempt, they found someone with the mutation who agreed to donate if necessary. However, at the time, a stem cell transplant wasn't really on the table because Timothy's leukemia was in remission and such surgery was considered very high risk. But the remission lasted only about a year, and by the end of 2006, his leukemia returned. And that was when Timothy decided to undergo the transplant. On the day of his transplant, he stopped taking his HIV medication entirely. So this way it would become clear if he was cured or not, because typically HIV therapy has to be taken continuously. If patient interrupts the treatment, the virus usually rebound to its previous levels, just like it did in Timothy's case when his therapy was interrupted earlier in his leukemia treatment. But not this time. Remarkably, 3 months after the stem cell transplant, HIV was undetectable in his body, and he was eventually declared cured of HIV. Unfortunately, his ordeal didn't end here. In 2008, his leukemia returned, and the doctors decided on second stem cell transplant, using again the same donor as the first time. The way Timothy Ray Brown describes his recovery process highlights why such therapy isn't a viable option solely to cure HIV, which again in this case, it wasn't the primary aim. It was a life-saving cancer therapy, and the HIV cure was more of a bonus. After his transplant, he became delirious, he nearly went blind, and he was almost paralyzed. He even had to learn how to walk again at a center for patients with severe brain injuries. Also, before he could even undergo the procedure, he had to have total body irradiation. So even if there were enough suitable donors, this procedure shouldn't be performed merely to cure HIV because of its extreme risks. In 2010, Timothy Ray Brown abandoned the Berlin patient nickname. He revealed his identity to the public and became an activist in the fight against AIDS. He really wanted to support the HIV research, so he agreed to have many tests done and also biopsies to further scientific understanding. And he remained HIV negative for the rest of his life. Unfortunately, later his leukemia returned once again, and he passed away in 2020 at the age of only 54. 11 years later, another successful case followed. Using the same naming convention, the Berlin patient was followed by the London patient, who became resistant to HIV infection after receiving bone marrow transplant to treat Hodgkin's lymphoma. In his case, the doctors were more cautious, so the London patient continued taking HIV medicine until day 500 post-transplant. But then, after stopping the HIV treatment, HIV still remained undetectable in his blood, and he is considered cured as well. And few more such cases have followed, but really only a handful. In total, I think only about 7 people have been cured of HIV or AIDS so far, since the procedure is risky, complex, and very expensive. And there are other reasons as well. For example, it is difficult to find appropriate stem cell donor. The Berlin patient had almost 300 matches, but that was unusually high. Finding a donor who is both a genetic match and carries the CCR5 Delta32 mutation is extremely rare, and it is limiting the number of potential candidates for this type of HIV cure approach. I saw a recent interesting paper that addressed how to approach this issue. In the paper, doctors were treating a mixed-race woman who had leukemia and was also HIV positive. And as part of her leukemia treatment, she needed a stem cell transplant. Oh, and just to be consistent, of course she's being referred to by the media as the New York patient. So, since she needed a stem cell transplant, her doctors hoped to cure her HIV infection as well. But for people with diverse ancestry, it is generally more difficult to find a good donor match. One way to overcome this limitation is to use stem cells from cord blood. The advantage is that cord blood requires less stringent matching, and there is also a low risk of rejection. So cord blood can be a great source of stem cells when finding a closely matched donor is difficult. However, there is also a disadvantage. Stem cells from umbilical cord blood are less efficient at generating a new immune system immediately after transplantation. So in this case, the doctors and researchers used a trick, or basically a two-part approach. They not only gave the patient a cord blood transplant, but also stem cells from peripheral blood of patient's relative. This relative didn't have the Delta32 mutation, so those cells were susceptible to HIV. But these additional stem cells were used to help engraftment and help the immune system to recover. Shortly after the transplant, the majority of immune cells in the patient were derived from the adult relative's stem cells. But over time, the proportion of these adult-derived cells declined, and the cord blood-derived cells, which take longer to fully engraft, eventually took over. The goal was for the resistant cord blood stem cells to replace her immune system in the long run. So even if there were initially more susceptible cells in her new immune system, in the end the mutated cells prevailed. The woman eventually stopped taking antiretroviral therapy and was later declared free of HIV and AIDS, becoming the first cured woman. When you think about it, what all these successful transplants have in common is that before the transplant, the patient's original immune system is destroyed. And since HIV infects immune cells, you might wonder if it's not enough to simply destroy the infected immune system and replace it with a healthy one. And indeed, this approach was considered and attempted. In the past, there were several attempts to control HIV infection by stem cell transplant without regard of the donor's CCR5 Delta32 status. But these efforts were not successful. In these cases, patients received transplants from donors with wild-type CCR5 cells, under the assumption that the new uninfected cells would replace their infected immune system. To test this possibility, doctors interrupted HIV therapy in 2 patients after they had successfully received stem cell transplant from donors whose cells were susceptible to HIV. It should be noted that this was an experiment the patients agreed with. Before stopping therapy, the researchers confirmed that they could no longer detect HIV in the patients, so the viral load was at least greatly reduced. They also observed that the patient's immune response to HIV began to weaken, a pattern similar to what was seen in the Berlin patient. After these promising results, they decided to proceed with the experiment and discontinued HIV therapy in these patients to basically see what would happen. But despite a significant reduction in the overall HIV reservoir, both patients eventually experienced a viral rebound once the treatment was stopped. For the first patient, HIV RNA became detectable in the plasma only 12 weeks after he stopped HIV therapy. Therapy was immediately resumed, but the patient still developed acute retroviral syndrome with symptoms like nausea, vomiting, headaches, or fever. And regaining control of the virus was also probably complicated by the fact that the patient didn't properly follow the therapy and he didn't take his medicine as he should have. In the end, he unfortunately had to be even hospitalized and his therapy had to be adjusted because he developed some drug-resistant variants of HIV. But luckily, he eventually recovered. For the second patient, the experiment initially proceeded more smoothly. But in the end, it also failed. 30 weeks after he stopped taking antiretroviral drugs, the patient developed symptoms and showed a rebound of viral RNA. These issues have resolved after he restarted the therapy. So in both patients, the infection rebounded, even though the virus had been undetectable before stopping therapy. It is believed that the rebound was caused by long-lived HIV reservoirs remaining in various tissues. Sequence analysis also confirmed that the virus originated from the same viral reservoir present before the stem cell transplant. So it really showed that some small pockets of the latently infected cells had persisted. So for this therapy to work, you really need to use cells from a carrier of the CCR5 Delta32 mutation. But as you may have noticed, I talked about the Delta32 mutation providing resistance to most HIV strains. Even in the earliest studies, when researchers isolated blood cells from people considered resistant to HIV, and when they tried infecting these cells in the lab, the cells were not resistant to all viral strains, only to some of them. HIV requires a chemokine co-receptor to enter cells. Often it's CCR5, but it can also be another chemokine called CXCR4. Thus, we distinguish CCR5 tropic HIV variants from CXCR4 tropic variants. And there are also some HIV variants that can use both co-receptors, and these are so-called dual tropic viruses. In one attempt to replicate the Berlin patient's success, another patient, of course nicknamed the SN patient, also received a CCR5 Delta32 transplant. But unfortunately, he experienced a viral rebound after interrupting his HIV therapy. This was because a minority of the HIV variants in his body were able to use the alternative CXCR4 co-receptor. So in his case, the therapy had failed because of these viral variants. Variants of the virus that use this second chemokine co-receptor typically appear later in the course of HIV infection. In approximately 50% of the patients, you can observe a shift in the co-receptor usage. And this shift correlates with disease progression. Early in the infection, a patient is predominantly infected with a CCR5 tropic HIV. But at later stages, these so-called X4 tropic variants can emerge. There are also notable differences among these variants in terms of the cells they infect. The CCR5 variants, which dominate early on, infect cells like macrophages, dendritic cells, or the CD4 positive T cells. These variants replicate more slowly and cause less cytopathic damage. CCR5 variants are selected for early in the infection. It's partly because they can better evade epithelial host defenses, so for example, they are less affected by defensins secreted by epithelial cells. And then there are the X4 HIV variants. In response to the HIV infection, the immune system generates neutralizing antibodies that target the HIV envelope protein. However, the envelope gene can mutate, which allows HIV to escape these antibodies. And such mutations can lead to the selection of X4 or dual tropic variants. The X4 variants predominantly infect T lymphocytes, but they can also expand infection to other cell types, such as B lymphocytes, NK cells, or CD8 T lymphocytes. They are also more likely to infect cells like astrocytes or neural cells via CD4 independent pathways, which can contribute to the spread of HIV in neural tissues, which happens during the late-stage infection. Before researchers performed the very first transplant aimed at curing HIV, the Timothy Ray Brown's Berlin patient procedure, they analyzed the viral variants in his body and confirmed that his virus primarily used the CCR5 co-receptor. They sequenced the viral RNA, which was in his body, and it showed that only 3% of his viruses were the X4 variants, so it was considered relatively safe. And in the end, these X4 variants luckily didn't recede his replaced immune system. Similarly, In the case of the London patient, doctors also started by confirming that he was infected with CCR5 tropic HIV, and they didn't find any X4 tropic variants. But in one of the cases, HIV cure attempt failed, even though the patient was confirmed to be predominantly infected with CCR5 specific viruses. The keyword here is predominantly, because when he stopped antiretroviral therapy after the transplant, the virus rebounded, and doctors observed a shift toward X4 tropic variants. So the virus managed to escape the therapy by switching co-receptors. So the CCR5 Delta32 mutation isn't a foolproof protection against HIV. And moreover, protection against HIV is probably not the reason this mutation was selected in the population, and it's more of a bonus effect. The estimates of its origin range anywhere from around 700 years ago to over 5,000 years ago. There are some interesting studies trying to pinpoint this timeline, but to be honest, I don't really understand the mathematical models well enough to have a firm opinion on who's correct. Still, it's likely on the older side because of recent and new discoveries of the variant in ancient DNA. The reason we believe HIV wasn't the driving force for the selection of this mutation is that HIV simply hasn't been in the population long enough. The human population, I mean. It emerged relatively recently, while CCR5 Delta32 was under evolutionary selection for much longer. Researchers suggest that maybe a different pathogen was involved. So we need to take a look at older diseases. For a long time, the leading candidate was plague, for several reasons. First, the mutation is common in Europe, where the Black Death had its most severe impact. Second, the plague had extremely high mortality rate. It is estimated to have killed 30 to 50% of Europe's population in the 14th century. So such mortality could exert intense selection, favoring any genetic variants that offer even slight survival advantage. However, other researchers argue that the timing doesn't fully align with the Black Death as the primary driver. And models suggest that plague alone wouldn't create enough selection pressure to reach the current approximately 10% allele frequency in Europe. Additionally, biologists tested whether CCR5 Delta32 confers resistance to plague in vitro and found no significant effect. So it probably wasn't the plague. Some researchers have proposed smallpox as the more likely culprit. Smallpox was persistent in Europe, causing frequent and severe epidemics from ancient times until the 18th century. It was endemic and widespread in Europe, but less common in Asia and Africa, which aligns well with the mutation's distribution. Smallpox also had a high fatality rate, approximately 30%, and tended to affect children, applying steady selective pressure. When I read about these speculations, I got frustrated by the lack of experimental evidence. I mean, why didn't anyone just test this mutation's effect on smallpox in vitro? And it took me a while to have the aha moment that such experiments aren't feasible anymore, because variola virus, the virus causing smallpox, is no longer worked with for safety reasons. There are only few labs in the world that even store the virus, so direct testing is practically impossible. So who knows if and when we will receive the final answer. Well, when discussing therapies that replace a person's immune system with CCR5 Delta32 carrying cells, we should also consider the potential negative effects. CCR5 plays a role in immune responses, particularly in inflammation. And it's known to be involved in the body response to infections like Mycobacterium tuberculosis or Coxsackie virus. But despite these concerns, no significant health issues have been observed in clinical studies of people who are homozygous for Delta32 mutation. These people appear to be healthy, potentially because CCR5 function is compensated by other chemokine receptors, or maybe because CCR5's role is redundant in humans. One notable concern is that homozygous Delta32 carriers may be more susceptible to West Nile virus. West Nile virus is a mosquito-borne virus that can cause fever and other symptoms, and in some cases, the infection leads to serious complications. However, the exact risk levels associated with the Delta32 mutation are still debated. So overall, this approach is considered relatively safe. But, safe or not, for the reasons I've already discussed, this approach to curing AIDS isn't likely to become widespread, and it will remain an option that can make life a little bit easier for few people. In the near future, I personally see far greater potential in the long-acting retrovirals, antiretrovirals, like lenacapavir, which I talked about in the last episode. And that wraps up my retelling of the Berlin patient's story. As always, thank you so much for listening all the way through, which makes me very happy. And I also want to thank everyone who has rated or recommended the podcast. You can find the episode sources in the description, and hopefully the next episode won't take as long, although in my defense, revising my paper basically required me to live in the lab. If you'd like to be notified about new episodes, feel free to follow the podcast on your favorite app or find it on Instagram. And once again, thank you for listening.